Hello, everyone. We're going to continue our discussion on inflection as we talk about what happens at a point of inflection. So a point of inflection is a point on the curve where there's a change in curvature or shape. Okay, now we've already seen this horizontal or stationary inflection, and we noticed that because the slope of the tangent at this point is 0, if I take the first derivative and set it equal to 0, and I do the sine diagram, and the signs don't change through that point, then I have a horizontal inflection point or a stationary inflection point. But a lot of curves have these more exaggerated points of inflection where we actually change from concave down to concave up or vice versa. That's called a non-stationary inflection point because the slope of the tangent at this point is not 0. We can say that there's a non-stationary point of inflection at x equals a if the second derivative at the value a equals 0 and the sign of the function of the second derivative changes at x equals a. Okay, so in other words, if I do a sine diagram with the second derivative and it changes from positive to negative or from negative to positive, I can say that that is a non-stationary point of inflection. And generally, we just say point of inflection referring to non-stationary inflections. We only say stationary if it actually is. We only refer to it as a stationary inflection if it's stationary. Okay, so the second derivative test says that if a curve is concave down on the interval S, then the second derivative is negative, and therefore we must have a local max. If the second derivative is positive on an interval, then my curve is concave up, and I must have a local min. Okay, however, if the second derivative at a particular value is equal to 0, then we likely have a non-stationary, we have an inflection point. It's stationary if the first derivative was equal to 0. It's a non-stationary inflection point if the first derivative is not equal to 0. So here is an example. I'm just going to put down a shade here to make it a little bit more manageable. So we have the function x to the 4 minus x cubed plus 3. And to work with the second, to find out about curvature, we need to do the first derivative and the second derivative. So I take the first derivative and I get x squared times 4x minus 3. And then I take the second derivative. Okay, and notice that for my second derivative, it's actually easier if I use this expanded form to find it. I like the factored form for later, but I like the standard form to help me find my second derivative, so I don't have to use the product rule. And then I factor it. Okay, so take the first derivative, factor it, set it equal to 0. Usually I do that part first. Okay, so here's my first derivative set equal to 0, and I have turning points at 0 and 3/4. I do my sine diagram, okay, and I notice that I've got a function that's decreasing, decreasing, and then increasing. So I know that if it's decreasing and then increasing, this should be a local minimum. Here, if I have a decrease and then a decrease, that suggests that this is probably an inflection point, okay, at a non-stationary inflection point. Then I'm going to go do my second derivative test to help me find the points of inflection, okay? So the first derivative test helps me find the turning points. The second derivative test helps me find points of inflection. So here's my second derivative. I factored it, set it equal to 0. I found my 2 points that are potential inflection points. And I set up my same sine diagram, except now I'm going to be finding the values of the second derivative. Okay, so the second derivative is positive between 0 and negative infinity, which suggests that my function is concave up. It is negative between 0 and negative 1/2. Sorry, between 0 and positive 1/2. My second derivative would be negative. Okay, if I pick, so it's concave down. And if I pick a value larger than 1/2, say 2, I'm going to have a positive times a positive, which is going to give me a positive second derivative, and therefore my function is concave up. Okay, so I could draw little shapes like that, or I can write the words. If I go from concave up to concave down, that suggests an inflection point when x is 0. If I go from concave down to concave up, it suggests an inflection point at x equals 1/2. And so I have 2 inflection points. I find the actual value of the point by plugging my x values into my original function.